This is slide number 56 and I am your presenter Asloob Mudassar. Imaging system frequency domain analysis. Before that we have discussed an optical system consisting of a single aberration free convex lens under monochromatic coherent illumination. Here we are going to discuss a more complicated optical system which consists of many optical elements including limiting apertures, convex and concave lenses, etc. lying between the object plane and the image plane under illumination by monochromatic and quasi-monochromatic light sources. So here we are going to discuss an optical systems which are rather complex and contains many optical elements, and also the limiting apertures are also contained in such an optical system, and the illumination that we shall be using will be monochromatic or quasi-monochromatic light sources will be used. Sources considered will be spatially coherent and spatially incoherent. We have explained the coherent and incoherent terms much earlier. Now the optical elements can be assumed to be lying within a hypothetical black box with its side facing towards the object plane, contains the entrance pupil, and its side facing the image plane contains the exit pupil of the system. For example, look at this diagram. There are two planes, zeta and eta plane as the input object plane, and we have the UV plane which is the image plane. And you see that in these two planes there are two planes also which we have labeled as XY plane. And you know that these are the two faces of the black box. So I have labeled a black box which has been shown in gray. So there are some optical components which we don't know what are the optical components inside that one. That's why we have labeled it as black box. But you know that the left face of the black box contains an aperture which we shall call as entrance pupil, and the right side of the aperture, right side of the black box contains an aperture which we call exit pupil. The X and Y are we have labeled the both sides of these black box. Both the ends of this black box has been labeled with the X and Y coordinate systems, and we shall be explaining these with a much greater detail today. So you see that both the coherent and incoherent imaging system will be analyzed in the frequency domain, and Fourier techniques will be applied throughout to explain the features of the coherent and incoherent systems. So we are going to discuss coherent systems, we are going to discuss incoherent systems, we are going to apply of course the Fourier techniques in order to analyze those systems in frequency domain, which means that we could analyze them in the Fourier domain. Now we shall be explaining this optical system in the following text. Model of imaging systems. The black box may consist of one or more physical apertures and may have some optics lying to its left side and some optics lying to its right side. So you see that the black box may contain some physically limiting aperture, maybe for example somewhere within the black box. And you know that we shall have some optics on the left side of that limiting aperture contained within the black box, and we may have some optics contained on the right side of that limiting aperture within the black box. The image of this physical limiting aperture through the optics lying on its left side is referred to as the entrance pupil, whereas its image through the optic axis lying to the right side is referred to as the exit pupil. So you see that assume that there is a limiting aperture within the black box. So the image of this limiting aperture on the through the optical systems, through the optical elements lying on the left side of the black box will produce the entrance pupil, and the optics on the right side of this limiting aperture will produce an aperture which is called exit pupil. So entrance pupil and the exit pupil are actually the images of the limiting aperture through the optics on the left hand side within the black box and on the right hand side within the black box. Entrance and exit pupils are also the images of each other through the optical elements lying between them. Entrance and exit pupils are therefore identical, and we have labeled their planes as the xy plane. So you see that here now the reason is clear that why we have labeled the two pupils, that is the entrance pupil and the exit pupil, by the xy plane. The reason is that both pupils are identical. That is, the entrance pupil is the image of the exit pupil through the optics lying on the left, and the exit pupil is the image of the entrance pupil lying on the right side of the through the optics lying on the right side within the black box. So entrance and exit pupils are the images of each other through the optics contained within the black box. And as we have stated, these two pupils are the image of the physical limiting aperture which is present in the black box, and the entrance pupil is the image of that limiting aperture through the optics lying on the left side of that physical aperture in the black box, and the exit pupil will be the image of the entrance of that physical aperture through the optics lying on the right side within the black box. Components within the black box may not necessarily be thin. Since the entrance and the exit pupils are perfect images of each other, it means that the passage of light between these two planes does not involve any kind of diffraction. So remember that we assume that no diffraction is present within the elements that are present in the black box. So geometric or ray optics is therefore adequate to describe the propagation of light between these two planes. Consider a point source located at the zeta-eta plane, and a spherically diverging wave is incident on the entrance pupil. So look at this figure. You see that a point source is located on the zeta-eta plane, generating spherically diverging wavefront, a part of which one has been intersected by the entrance pupil. Okay. If the entrance pupil limits the spatial extent of the input wavefront, it will act as a source of diffraction. So you see that this entrance pupil will produce diffraction when the diverging spherical wave incident on this aperture is greater in spatial extent in comparison with the dimensions of the entrance pupil. Light will then propagate following geometrical optics rules towards the exit pupil. The light will then leave the exit pupil following a physical optics rule towards the image plane. So you see that here we have shown that a spherically converging wavefront is leaving the exit pupil and of course is focusing at the image point, at an image plane in the form an image point. Okay. The limit to spatial extent of the input wavefront by the entrance pupil, by physical aperture, or by the exit pupil, all these are equivalent with each other. The diffraction caused by the entrance pupil is equivalent to the diffraction caused by the physical limiting aperture or the diffraction caused by the exit pupil of the system. So you see that with respect to all these three pupils, the physical aperture and the entrance pupil and the exit pupil, the diffraction are equivalent with respect to these three apertures. All these approaches yield identical results. As all pupils are identical, we shall consider diffraction caused by the spatial limit to outgoing wave front at the exit pupil. So you see that we shall be only concentrating on the exit pupil, and the wave fronts which are leaving the exit pupil we shall consider them only with respect to the exit pupil. The exit pupil will now referred simply as the pupil for the rest of the course. So whenever we shall be talking about the pupil of the optical system, it means that we shall be talking about the exit pupil of the imaging system. A perfect point image means that a perfect diverging wavefront leave a perfect diverging spherical wave at the entrance pupil is converted to a perfect converging spherical wave at the exit pupil. This diffraction limited behavior of an imaging system is extended only to a finite region of the object and image plane. Real imaging systems are not diffraction limited if larger parts of the object and image planes are considered. The optical system shown in earlier produces sharp image point, and such a system is referred to as aberration free system. So you see that in our optical system, for example in this case, you will see that a perfect spherical wave is incident on the entrance pupil, and similarly a perfect converging spherical wave will leave the exit pupil. So it will also produce a sharp image of the point source located at the object plane, that is at the zeta eta plane. So a sharp image point will be located at the UV plane corresponding to the point object at the zeta eta plane. No diffraction means that the system pupils are much larger and do not limit the spatial extent of the wavefronts. The image point will be an exact replica of the object point if we assume a unit magnification system. So under a unit magnification system, the image point will be an exact replica of the object point. Diffraction is the main cause of limit to resolution of an imaging system. We shall consider diffraction due to exit pupil in this course. Let's reproduce the expression for the impulse response of a system consisting of a single imaging lens having lens pupil function p of xy. So you see that we are listing down the impulse response of the system, that is kappa at the coordinates u minus zeta and comma v minus eta. And you know that this is not lambda, but actually this is actually eta. So kappa as a function of u minus zeta and v minus eta is equal to a over lambda zi, where zi is the image distance, and double integration of contained p of xy, that is the pupil function of a single lens multiplied by e to the power minus iota 2 pi over lambda zi, and within the curly bracket and within the parenthesis we have u minus zeta multiplied by x plus v minus eta multiplied by y, and then we have dx and dy. And you know that here we can read zeta as inverted hat and eta can be read as inverted hat. So we shall not be reading these inverted term again and again, inverted hat terms. We are just reading zeta and eta. So this is equation 1, you know, and now we proceed further ahead. So zeta is equal to m times zeta and eta inverted hat is equal to m times eta, where m is the magnification of the system. So you see that these two substitutions helped in the writing down kappa u minus zeta inverted hat v minus eta inverted hat for space invariant system. And you know that we are using a is equal to small a over lambda z naught, and here we are setting small a is equal to 1 because small a is the strength of the point source at the object plane, and we have assumed that the strength of the object of the point source at the object plane is unity. That is why we have chosen a is equal to 1. and the amplitude of the field at that point is equal to capital A is equal to small a over lambda z naught. And you know that this is the amplitude of the wave at the location after a distance z naught from the location of the point source, that is at the location of the entrance pupil. For a coherent imaging system, the field at the image plane is given by. So now we are writing about the field of the coherent imaging system due to a single lens. So double integration of the kappa inverted kappa, and within the parenthesis we have u minus inverted zeta comma v minus inverted eta, and we have ug, which is the geometrical optics image, and you know that it has a coordinates zeta inverted and eta inverted, and the integration is with respect to d zeta inverted and d eta inverted. And you know that we can write this integral, identifying this integral as the convolution integral. We can write the integral in the symbolic form as kappa inverted as a function of uv convolved with the uj, which is the geometric optics image, as a function of uv. So this UG has been measured at the image plane because UV are the coordinates at the image plane. But you know that while we record this amplitude, which is UG, we ignore the diffraction, and you know that it will convolve with the kappa, and ultimately UI will contain the aberrated image, will contain the image which involves diffraction. So equation 2 is so left hand side will give you the amplitude at the u and v points of the image plane in terms of the convolution between the kappa and the geometric optics image. Now you see that where kappa inverted kappa is equal to u minus zeta inverted comma v minus eta inverted is equal to kappa of u minus zeta comma v minus eta divided by the absolute value of the magnification of the system. And you know that this is the normalized amplitude point spread function. So kappa, you know that kappa inverted is the normalized amplitude point spread function with the magnification capital M is equal to minus zi over z naught is the system magnification. Earlier we have defined the geometric optics image UG at the coordinates u and v, and which we are reproducing in equation number 3. So UG, that is the geometric optics image at the coordinates u and v, is equal to 1 over m mod and u naught of u over m mod comma v over m mod, where u naught is the field at the object point. And you know that then u naught with the coordinates u over m mod and v over m mod now is the geometric optics image giving you the field at the image plane. So this whole quantity on the right hand side will give you the field which we record as the geometric optics image as given in equation number 3. The amplitude point spread function can be written as given below, following equation number 1. So you see that we can write kappa as a function of u and v equivalent to a over lambda zi double integration of p of x comma y e to the power minus iota 2 pi over lambda zi and u into x plus v into y. Integration is with respect to dx and dy. And you know that if in the left hand side, if you change the arguments of the kappa by u minus zeta inverted, then you know that on the right hand side on the exponent u will also be replaced by u minus zeta inverted. And if you replace v by v inverted minus eta, then you know that this will also takes place on the exponential side, and then v will be changed by v minus zeta inverted. So you see that now the right hand side can be written as, this integral can be written as a over lambda zi into the Fourier transform of the exit pupil function. And you know that p of xy for a single lens for a single lens p of xy is the entrance pupil as well as the exit pupil as well as the limiting aperture or the physical aperture of the system. So for a single lens p of xy will stand for all the 3 apertures, that is for the entrance pupil, that is for the exit pupil, and that is for the physical aperture of the system. So we can say that p of xy is actually the we can take it because you see that as mentioned earlier, we shall be using the exit people term. So we have the kappa is equal to a over lambda z I multiplied by the Fourier transform of the exit people function as given in equation number 4. So here p of xy is the exit people we are considering. That is, the amplitude point separated function is proportional to the Fraunhofer diffraction pattern of the system exit people. And you know that in the Fraunhofer pattern, what we have is that we have the Fourier transform of the people function, which we refer to as the Fraunhofer diffraction formula. And you know that this kappa is actually on the right hand side, we have an integral that, like that one, because we have the Fourier transform of the exit people. It means that we have the Fraunhofer diffraction pattern of that system. The normalized PSF, which is inverted kappa as a function of u minus zeta inverted and v minus eta inverted, has built-in dependence on the system magnification m mod. Dropping m mod, that is writing kappa as a function of u minus zeta inverted and v minus eta inverted instead of inverted kappa, having a coordinates u minus zeta inverted, v minus eta inverted would not change the physics. From now onward, we shall be using kappa, not kappa inverted, instead of kappa inverted. Under this scenario, the image amplitude can be written as given following equation number 2. So you see that here we have written the same equation but with kappa, not with kappa inverted. And you know that we have also the geometric optics image present in that one, and we can write this integral as the convolution of a kappa, with the geometric optics image as given in equation number 5. That is, for a diffraction limited system, the image field ui as a function of u and v may be regarded as equal to the convolution between the geometric optics image ug of u comma v and the system amplitude point separate function kappa as a function of u and v. And you know that convolution is a commutative operator, so you can convolve kappa with ug or you can convolve ug with kappa, both are equivalent. Now let's talk about the polychromatic illumination and imaging system. There are two types of illumination, coherent and incoherent, and thus two types of imaging systems, coherent imaging system and incoherent imaging system, based on the types of illumination that we are using. Coherent systems are those in which there is a fixed phase relationship with time in space among parts of a field on a plane. And in incoherent system are those systems in which the phase relationship vary with time in space among the parts of a field on a plane. If on a plane at a single point the phase value stays the same for a period of time delta t, then the source is said to have temporal coherence of length equal to c delta t. If the relative phases and amplitudes, which we refer to as the phasor amplitudes, at different points on the plane are perfectly correlated, and if this correlation stays with the time, the optical field is regarded as coherent, or more accurately as spatially coherent. But if these phasor amplitudes are uncorrelated with time or change randomly, we refer this field as spatially incoherent. So you see that here we clearly explain what are coherent or spatially coherent and or what are incoherent or spatially incoherent fields. A perfect monochromatic source does not exist. However, a laser having a narrow band with a single dominant wavelength may be regarded as a monochromatic source. A point source generated from a monochromatic source may be treated as a perfect coherent source. So consider that a point source, we have used the word, a point source generated from a monochromatic source may be treated as a perfect coherent source. 4 pinholes illuminated with a spatially coherent spherical wave front acting as 4 point sources are shown. So you see, now look at this diagram. there are four on the object plane. We have an opaque aperture which contains 4 pinholes. And you know that this aperture has been, this is the object plane, aperture has been illuminated with a spherically diverging wavefront generated from a single point source. It means that the wavefront is spatially coherent, which illuminates the 4 pinholes. And you know that this information which will pass through the optical black hole or optical black box, and you know that the waves will be generated from the optical black box will generate 4 spherically diverging 4 spherically converging wave fronts, which will converge at 4 different points. So each point on the image plane corresponds to one converging spherical wavefront. So it means that while passing through this optical black box, 4 converging wavefronts have been generated corresponding to the 4 pinholes at the input. So 4 images are formed. And you know that if these point sources, that is these 4 pinholes generating are acting as 4 point sources, and you know that the black box has given the images as 4 point sources on the image plane. Four pinholes illuminated with a spatially coherent spherical wavefront acting as 4 point sources are shown. Elements contained within the black box form 4 output impulse responses which are spatially coherent. That is, the phasor amplitudes are spatially coherent for this system. These amplitude impulse responses are therefore added in the overlapped region on the basis of complex amplitudes to find the net field at the image plane. In this figure we have shown these point sources or the 4 pinholes acting as 4 point sources are very well separated from each other, and similarly the corresponding images, the 4 point sources at the 4 images are also very well separated. But suppose that if the 4 pinholes at the object plane are very close to each other, then you see that it might be possible that there is an overlap between the 4 image points at the image plane. And when there is an overlap, then you know that in the overlapped area, we shall add the amplitudes, not the intensities. So the amplitude addition will take place because the system is coherent system. So coherent imaging system are therefore linear in complex amplitudes. That is the phasor amplitudes will be added. For a coherent illumination, the phasor, which we denote as u of p, containing the spatial part of the wave, is given as given in equation number 6 and 7. So this small u, which represents an incoherent system. So you see that incoherent beams will be represented by small alphabets. For example, we have used small u as a function of a position and time, that is p comma t, that is equal to a of p, that is amplitude as a position dependent amplitude, into e to the power minus omega t plus phi. And you see that can be written as u of p into e to the power minus omega t. And you know that here we have what is u capital U of p, that has been written in equation number 7. So capital U of p is equal to amplitude at the position p multiplied by phase term, which is e to the power minus iota phi of p. So the phase phi of p is the phase at the position p, and a of p is the phase at the position p, and u of p is referred to as the phasor at the position p. So incoherent light is obtained from the extended sources. 4 pinholes at the object plane are illuminated by a wavefront from an extended source. So this is what we are talking about, this figure. So you see that in this figure an extended source is present, which is generating a complex wavefront. This is not a perfectly spherical wavefront, but it is a complex wavefront. So this will illuminate the object plane, and of course the object plane will generate the wavefronts which are also complex, and those wavefronts will pass through the optical black box, and of course at the end the wavefronts which will be generated, though such wavefronts will be converging, but they will not be perfectly spherically converging wavefronts, but of course some complex type of those wavefronts are obtained over here. So incoherent light is obtained from the extended source. So you see that here this is an extended source generating incoherent wavefront, and 4 pinholes at the object plane are illuminated by a wavefront from an extended source. Phasor amplitudes from these pinholes are random in time. So the phasor amplitudes are random in time, that is time dependent. The field within each impulse response is self-coherent, but the fields of these 4 impulse responses are incoherent with respect to each other. Since you know that these holes are very small, these pinholes are very small, so these will act as small point sources, and the waves generated by these 4 point sources will be coherent by themselves. In themselves they are coherent, but with respect to the neighboring sources they are incoherent. So this is what we have written, that is the field within each impulse response is self-coherent, but the fields of these 4 impulse responses are incoherent with respect to each other. The system may be regarded on the basis of illumination as incoherent imaging system. The region where the impulse responses overlap cannot be added on the basis of complex amplitudes, but must be added on the basis of intensity, because the system is incoherent. It is because the intensity corresponding to each impulse response is proportional to the intensity of the corresponding object point source. An incoherent imaging system is therefore linear in intensity. So here the intensity of these one will vary according to the intensity of according to the variation in intensity at the 4 pinholes. But you know that in the previous case where we have discussed this figure, where it was illuminated with a perfect spherical diverging wavefront, then you see that the amplitude at these 4 points, that is at the image point, will vary with the amplitudes variation at these 4 points. So this system is linear in amplitude, but you know that here this system is linear in intensity, because the output intensities will vary with the intensities of the input signals. Narrowband polychromatic illumination means that spread or bandwidth of frequencies is much smaller in comparison with the central frequency in the bandwidth. So you see that when we consider the bandwidth of a narrow band polychromatic source, it contains many wavelengths, and you know that there is a central wavelength, the band which has some frequency. The bandwidth of that profile of the wavefront is actually smaller in comparison with the central frequency. That's why we say that the bandwidth or the spread of the frequencies is much smaller than in comparison with the central frequency in the bandwidth, and such sources are referred to as the narrowband polychromatic sources. A laser source which has more than 10 longitudinal modes, that is more than 10 different frequencies, may be regarded as narrowband polychromatic source. If in an incoherent illumination, phasors not only depend on spatial coordinates but also have temporal dependence. The phasor of a complex field which we denote as small alphabet u of u as a function of position and time in an incoherent imaging system is therefore given by equation number 8. and you know that here we have also time dependence. So small u as a function of a position and a time is equal to capital A as a function of a position and a time multiplied by e to the power minus iota omega inverted omega or omega average, you can say, multiplied by time plus phi of phi as a function of a position and a time. And you know that here we have separated the special part of the beam, and we have separated the time dependent part of the beam. So u of p comma t is actually the phasor of the incoherent system, but you know that here it also depends upon time, and there is also a time dependence which we have as e to the power minus iota omega t. And you know that on the right side we of equation number 8 we have u of p comma t multiplied by e to the power minus iota 2 pi nu t. You may consider nu as the average frequency or the central frequency of the band of the polychromatic light source. And you know that now this u which is the phasor of the incoherent, which is the phasor is a function related with the position as well as time. So nu prime or the nu average is the mean or the central frequency of the polychromatic incoherent beam, and capital U of pt is the time varying phasor of the wave. The behavior of an incoherent imaging system is determined by the time varying nature of its complex phasor. Statistical averaging is thus required to determine the incoherent field at a single point in the image space. With the coherent system, the instantaneous measurement of amplitude is the same as the average of that field. But you know that in the incoherent system, if the instantaneous field measurement is different from the average field. So that's why in incoherent systems we always talk about the average measurement or the statistical averaging of the field that we are measuring. A definite statistical relationship between the phasors at various object points or various image points under illumination by polychromatic light source may exist. So you see that here we shall talk about the statistical relationship between the phasors at various object points or various image points. So you see that we shall be talking about the statistical relationship between the points of the images of the 4 points that we have shown in the above diagram under the illumination by polychromatic light sources. So for such light sources we shall be talking about the statistical relationship between the phasors of those 4 points at the image plane. The image field is thus determined by the time averaging, which is greatly influenced by the statistical nature of phasors in a polychromatic illumination. The main contribution of the amplitude impulse response dependence is determined by the central frequency and not by the frequencies around central frequency nu average or nu prime. The amplitude impulse response or amplitude point spread function is therefore considered as independent of time. So you see that even in an incoherent system, the amplitude impulse response will be the same as we use for the coherent system, or the amplitude impulse response for the incoherent system is the same as for the coherent system. That's why we have used the word amplitude impulse response, and or the amplitude point spread function is therefore considered as independent of time. The amplitude point spread function of the coherent imaging system can thus be used for the incoherent imaging system under narrow band assumption. The imaging equation for the coherent system given in equation number 5 can be adopted for an imaging system with a narrow band polychromatic illumination as given below. So you see that we have written this equation for a narrow band polychromatic source, and you know that we have adopted it from the equation given for the coherent source, but you know that the difference is that we have for the incoherent system, that is the UG, which is the incoherent field at the image plane, is also dependent upon time. And you know that we have t minus tau as the time delay. The field UG will appear in comparison with the UI of u as of UI that is the input field at the image, that is the field at the image plane as a function of u comma v comma t. So this field is related with the delayed time t minus tau of the geometric optics field. And you know that this kappa that we have written is independent of time, as we have explained above, but you know that the geometric optics field is dependent upon time. So it means that the field we are measuring at the image plane, even though for a narrow band polychromatic illumination, is also time dependent, as in equation number 9 on the left hand side, and also within the integral on the right hand side, in which UG also contains time dependence, though as t minus tau. So tau is the time taken by an optical disturbance in moving from the object plane, that is from the zeta eta plane, to the image plane, which is the UV plane, where UI as a function of u comma v comma t is the instantaneous image field at the image point u comma v. The image intensity can be found by taking the time averaging of the absolute square of the image field with integration time of the detector much greater than the reciprocal of the optical bandwidth of the polychromatic beam. The intensity is thus given by equation number 10, that is the intensity at the image plane as a function of u and v is equal to the time averaging of the absolute value of the complex field at the u comma v comma t, that is at the image plane as a function of u comma v comma t. So you see that this u, the absolute value, can be represented as ui multiplied by its complex conjugate, and the time averaging symbol has been shown, and this time averaging is such that the time averaging is much greater than the reciprocal of the optical bandwidth of the polychromatic source. Now, using equation number 9 into equation number 10, we obtained the following intensity expression. You see that in equation number 9 we have calculated the field. This field is now going to be plugged in the expressions of equation number 10 to find out the intensity. So you see that here we have two integrals, because one integral is because we have two set of integrals. Both integrals contains limits from minus infinity to plus infinity, and you know that when we combine the two integrals, we have to change the variables from d zeta 1, d eta 1 to d zeta 2 and d eta 2. And you know that we have to change all such variables for the two integrals, so that the our variables remain isolated with respect to each other. So you know that one integral will contain the variables zeta 1 prime, zeta eta 1 prime, and the other is zeta 2 prime and eta 2 prime. And similarly we shall have, and you know that we have in the integral, in the second integral we have the average, we have the time averaging of the complex of the field, which is UG multiplied by the complex conjugate of UG. And you know that we have also taken the time tau 1 and tau 2 there, because in the formation of UG, the time taken from the input image plane to the output image plane is tau 1, and for the complex field the image is tau 2. So the two images may be different, as in equation number 11. So you see that in equation number 11 we have the intensity expression for the incoherent imaging system when we are using narrow band polychromatic sources. But you know that the kappa in both these expressions is independent of the time. We have kappa, and we have also shown the complex conjugate of kappa. We have shown UG, and we have also shown the complex conjugate of UG contained within the time averaging notation. The product kappa with its complex conjugate will be non-zero only when two image points, one located at u is equal to zeta 1 prime, v is equal to eta 1 prime, and the other point u is equal to zeta 2 prime and v is equal to eta 2 prime are very close to each other. So this product, that is the product between two kappa, will be non-zero only when the two image points which we have mentioned are close to each other, that is there should be some overlapping between them. The two time delays tau 1 and tau 2 can then be taken equal or equivalently can be dropped from the expression in equation number 11 only when the 2 point sources are very close to each other. Under this assumption we can drop the time, or we can set the time between or we can set the time tau 1 is equal to tau 2 is equal to tau. We can rewrite equation number 11 in the following form by introducing a new quantity Jg. So you see that in equation number 1 we shall be introducing Jg as a function of zeta 1, zeta 2 and zeta 2 and eta 2. So Jg has parameters, 4 parameters, zeta 1, eta 1 and zeta 2 and eta 2 for equation number 11. So what is the Jg? Let's explain. So you see that now in equation number 11 we have replaced the terms which were contained in the time averaging, that is the time averaging of Ug multiplied by its complex conjugate has been replaced by Jg as a function of zeta 1, eta 1 and zeta 2 and eta 2 and as in equation number 12. Where Jg as a function of zeta 1, eta 1 and zeta 2 and eta 2 can be written as the time averaging of Ug as a function of zeta 1, eta 1, comma tau, and Ug star as a function of zeta 2, comma eta 2 and t as in equation number 13. So you see that equation number 13 gives you the expression of Jg in explicit form. What is Jg? Jg is referred to as the mutual intensity. It is physically related to the degree of spatial coherence of light between two image points. So mutual intensity, it is referred to as the mutual intensity, and it is physically related to the degree of spatial coherence of light between the two image points. So degree of coherence, of spatial coherence. So degree of spatial coherence between the two image points. So it is a very important quantity. If Jg is high in value, this would mean that the points zeta 1 and eta 2 and zeta 2 and eta 2 have phasors close to each other, or the light at these points has a higher value of spatial coherence. But if Jg is close to 0, it means that the phasor at the 2 points are uncorrelated and change randomly, and thus the spatial coherence is very low or nearly 0 between the 2 points. The intensity expression given in equation number 12, that is this equation which we have given in equation number 12, the intensity expression. The intensity expression given in equation number 10 was written when the object in an imaging system was illuminated with a narrow band polychromatic light source. In the next article, we shall convert this intensity expression for the coherent case. So you see that this is the end of slide number 56.